Hello everyone. Today we are going to understand how to calculate oxidation states of group 16, 17 and 18. I might be a bit overestimating on the concept, but I assure you once you go through this video, you can calculate oxidation state of any element in any group. Okay, so let's get started. For this to remember, we need to know something about Aufbau principle, through which we can actually gauge upon the general configuration. If Aufbau principle is something you're hearing for the first time, I would refer you to my video on Aufbau principle first. Make sure you go through that video, understand how configurations are done for every element, every group. What is the process that we follow? How do we put in the electrons? Which shell, subshell is used? All those things can be taken up by Aufbau, which I'll be linking above. Okay, now we are looking for group 16, group 17, and group 18. Correct. Now, group 16's, your general configuration from Aufbau we get is NS2, NP4. Group 17 general configuration NS2, NP5. And group 18 general configuration is NS2, NP6. Now, let's say you don't remember it quite well, no problem. Let's try to take one example each. We have oxygen, famous element of group 16, atomic number 8. We have fluorine, group 17, atomic number 9. And we have neon, group 18, atomic number 10. Let's see the configuration of these three elements, okay, to justify the general configuration. This is 1s2, 2s2, 2p4. How do we understand this configuration? Using Aufbau, okay? So 2 plus 2 is 4, 4 plus 4, 8. Here 1s2, 2s2, 2p5, 2 plus 2, 4, 4 plus 5, 9. Here we have 1s2, 2s2, 2p6, 2 plus 2, 4, 4 plus 6, 10. Okay, so can you all see this S2 and P4? These three are P block elements, right? P block group. So they are bound to end in P, right? So you can see over here S2, P4. Okay. See here S2, P5 ending in S2, P5. That's why general configuration NS2 and P5. Ending in S2, P6. That's why general configuration S2, P6. Okay, so one by one, we are going to pick up the groups, and with two examples each, we are going to understand how oxidation states can be understood, or how we can even understand, to go about oxidation state for any element for that matter. Okay, let's pick up with the first group. The first group that we are looking at is group 16. Okay, group 16, we have the general configuration NS2 and P4. So let's say let A be an element. Let A be an element in group 16. We are finding the general configuration, general oxidation state. So let A be an element over here. What is the configuration? NS2, NP6. Do we have any electrons in d orbital? No. So it becomes ND0, no electrons in d orbital. How do we represent this? See, it's not NP6, it's NP4. Okay, NP4. So here it becomes 2, here it becomes 1, 2, 3. Hans rule. Pauli's exclusion principle. We need to remember all these things. First, fill all the orbits, all the orbitals or boxes, one each, and then start pairing them up. Okay. Now, what happens over here? Whenever we are looking at oxidation state, how do we go about it? See over here. We have two unpaired electrons over here, correct? So if two electrons are lost by this element, what charge would this element gain? +2. So what does that help us understand? That oxidation state can be best understood with unpaired electrons. You can only pair the unpaired electrons, you can only lose the unpaired electrons. So as many unpaired electrons as you bring to the table, that can be your oxidation state. Okay, let's see another one. Okay, if there are no originally unpaired electrons, we can unpair them. Okay, so this is how it looks. What if we unpair this electron to this free orbital? What would happen? We would get one electron over here, and this originally paired electron would get unpaired. Now let's calculate how many unpaired electrons we have. 1, 2, 3, and 4. How many electrons can be lost? 4 electrons. What's the charge? +4. Let's see another thing. I think we still have paired electrons on our plate. We can unpair them, right? We can unpair them. How can we unpair them? There is a free space over here. Put your electron, unpair it. Okay, so when you unpair, that one electron comes over here. Correct. How many unpaired electrons are we looking at? 1, 2, 3, 4, 5, 6. 6 electrons can be traded by this element. So what are the 3 oxidation states of any element in group 16? +2, +4, +6. This is how you get that number. Okay, in textbook, they have directly given you the numbers, a bit problematic to understand how you're getting them. This is how we find oxidation state. Okay, so this becomes A +2. Then you have A +4. And you have A +6. Okay, this is only about losing electron. Group 16, 17. Examples: oxygen, sulfur, fluorine, chlorine. What are they? They are electronegative species, electronegative elements. And what is the main agenda of electronegative elements? They have the capability to gain or attract electrons. So what is the other way of representation? Let's see, we have NS2, NP4. These electrons, because they are highly electronegative, they can even gain electrons, right? Let's say that they gain 2 electrons. They gain 2 electrons. What would be the charge? If you lose electron, you get a plus charge. If you gain electron, you get a minus charge. Now, do you understand why we represent oxygen as O2 minus, sulfur S2 minus? This is the reason. How do we represent this element? A minus 2. Now, one more way in which we can work. Very rarely occurring way, but yes, it's a possible way. That is, we have NS2, NP4. Let's say rather than losing 2 electrons, we only lost 1 electron. So it becomes +1. Rather than gaining 2 electrons, we gained only 1 electron. It becomes -1. Rarely occurring names, rarely occurring species, but yes, they are prominent. A +1, A -1. Okay, so what all are the common oxidation states found in our group 16? +1, -1, -2, +2, +4, and +6. Okay, these are the oxidation states of group 16. Now, take a moment. Take your group 17, NS2, NP5. See how it works. Whether you're able to find the oxidation state without memorizing it. Okay. Let's take an example in group 16 itself. Let that be sulfur. Okay. Sulfur atomic number is 16, so configuration goes as 1s2, 2s2, 2p6, 3s2, 3p4. Okay, again you can see ns2 and p4 is constant. Let's try it. Okay, we have sulfur. Let's see the ground state of sulfur. It is what? 3s2, 3p4. Are there any electrons in 3d? No, so 3d 0. So we have 3s2, 1, 2, 1, 2, 3, 4. Okay, same agenda again. Okay, what if we gain electrons? If we gain 2 electrons, the charge becomes -2. Correct. What if we lose electrons? So how many electrons can we lose initially? Initially, there are 2 unpaired electrons. So we can lose these 2 unpaired electrons. Becomes +2. What other thing can be done? Start unpairing the paired electrons. When you start unpairing the paired electrons, you have some space, right? There's a d orbital vacant. So what do? You unpair this electron and you put the extra one over here. So now how many unpaired electrons? 1, 2, 3, 4 plus 4. Correct. Are there any other paired electrons? Yes, we have one more paired electron which we can unpair. 1, 2, 1, 2, 3, 4. This unpaired electron can again be brought up into this free space, correct? So you remove it, you include it over here. How many unpaired? 1, 2, 3, 4, 5, 6 plus 6. So how many oxidation states are we seeing for sulfur? For sulfur, we are seeing 4 prominent. S2 minus, S2 plus, S4 plus, S6 plus. If you have learnt about the oxoacids of sulfur, where you can see 6 bonds attached to sulfur atom. Now you'll understand why 6 bonds are attached, because there is a +6 parameter for it, right? It can give away 6 electrons, or it can bond with other 6 atoms. It can do a lot of things. So these oxidation states help us understand what can be the nature and character of a particular element as well. How much it can give away, how much it can take in, what reactions it can go for. Okay. Now I won't say problem, but one small difference which comes over here is with the first element of group 16. Oxygen, atomic number is 8, right? So it becomes 1s2, 2s2, 2p4. Now, according to Aufbau principle, D block or D electrons start from third orbit onwards, right? So when you go to 1, it's only 1s2. Second orbit, 2s2, 2p6. Third orbit onwards, it is 3s2, 3p6, 3d10. So here in second orbit on number 2, we do not have any d orbital vacant. There are no d orbitals. Okay. So what is happening? There is no d. We do not have any d orbital over here. Understanding? We have only 2s2, 2p4. There are no d orbitals. And why is that happening? Because d orbitals start appearing from third orbit onwards. From third orbit onwards. That's why in sulfur we had 3p2, 3s2, 3p4. So we could add our d orbitals over there. But in second one, we cannot. Okay. So let's see how oxygen will differ. Okay. Oxygen has 2s2, 2p4. 2p4. Correct? So what can happen? Two electrons can come in. Oxygen will get a charge of -2. Correct? What is another scenario that can happen? Again, there is no d orbital, so I'm going to put a cross over here. Okay, what else can be done? 2, 2, 2, and 2. There could be a chance that oxygen might lose these two electrons. So it will gain +2 charge. Mind you, unlike sulfur and other elements of group 18, there is no space for oxygen in d orbitals to unpair the paired electron. There are no d orbitals for unpairment. So there is no point of unpairing these electrons. There is no space for it. So these are the only two numbers we can gamble with. Another rarely occurring, what we can say, oxidation state would be, we have this, we have P4, and like the last time, if suppose one electron is lost, it becomes +1. If you gain one electron, it becomes -1 again. Very rare phenomenon, but yes, that can happen. Okay, so now try to relate it with something given in your textual matter. Why oxygen shows only 4 oxidation states, whereas others show plenty? Why +4 and +6 are not valid for oxygen? Okay, what can be a good question which can be formed? Why O +4 and O +6 are not possible? So the reason is given just on the next side, okay, because d orbitals are absent in oxygen. Okay, very famous question asked. Why is that happening? Because d orbitals are absent in oxygen. Okay, so if d orbitals are absent, higher oxidation states cannot be achieved. This summarizes our group 16 oxidation states and how we can remember them. Okay. Next one we have is group 18. We have group 17. Group 17 configuration is NS2 NP5, right? So let A be an element in group 17. Let A be an element in group 17. So how do we represent it? We'll represent it as A, NS2, NP5, and D0. NS2, NP5, NP5. We have only one unpaired electron over here. Okay, we have only one unpaired electron. So if this unpaired electron leaves, we get 1 plus. All other are paired. So we start unpairing them one by one. Correct? So we have 2, 2, 2, and 1. Unpair this. Okay, when you unpair, you get a higher number. How many unpaired electrons do we have now? 1, 2, and 3, right? So it becomes +3. Do we have more paired electrons? Yes, we do. So what are we waiting for? Keep unpairing. If you have understood, pause the video over here. Do it by yourself. Then resume. Check whether you're able to understand. Another unpairment. Another unpairment. What happens? From here, it has lost to there. Okay. So how many unpaired? 1, 2, 3, 4, 5. So what is the oxidation state? +5. Okay, any more paired electron? Yes, we do. We do have it. Okay, so this is 2. 1, 2, 3, 4, 5. What is the drill? Unpair the paired electron. Unpair the paired electron. Now see how many unpaired electrons? 1, 2, 3, 4, 5, 6, 7. What is it? +7. So what are the general oxidation states of group 17? +1, +3, +5, +7. Oh, we are forgetting about one. Group 17s are highly electronegative. What are they? They are highly electronegative. They require only one electron to make them stable. So how can we forget adding one electron? -1 charge. We can't forget -1 charge, right? So what are the oxidation states seen? A +1. We have got +3. We have got +5. We have got +7. And we have also got -1. So general oxidation states of group 17 are +1 -1, +3 +5 +7. Okay, simple, right? First you calculate or first you try to identify how many unpaired electrons. So that becomes your base or that becomes your oxidation state. And then if there are any paired electrons, you keep unpairing them. When you keep unpairing them, you will also get the oxidation numbers or oxidation states of your elements. Let's take an example. Which example do we take? The most famous of elements, chlorine, atomic number 17. What is it? 1s2, 2s2, 2p6, 3s2, 3p5, right? So let's see, 2, 2, 4, 10, 10 plus 2 is 12, 12 plus 5, 17. Yes, we are going good. Okay, so we have chlorine. We have got 3s2. See, third orbit meaning d orbital is present but vacant. It does not have any electrons in it. So 3s2. Okay, if you have understood how to do this, pause the video. Do it by yourself. What happens over here? If we take one electron, we add one electron. What is the oxidation state? -1, right? What if we start losing the electrons? How the things would look like? Let's see. Okay. So I'll just add up all the possible configurations over here. So you can take some time in understanding what states can be formed. Okay. Okay, then I feel it would be pretty much easy to give the states. Okay. So since there is only one unpaired electron, it can be lost. You get +1. What happens next? In the next one, this paired electron can come over here. Right, it can come over there. What will it become? How many unpaired electrons do we have now? We have 3 unpaired electrons. 1, 2, and 3. Becomes +3. What else? What else do we have now? Here we have got again unpairing. How many unpairing can we see? Yes or no? This was paired. It came over here. What is now the oxidation state? It is +5. What happens in the next one? What happens in the next one? Originally we have what? We have this much. You are again unpairing. So when you unpair, all of them become unpaired. And what is the oxidation state? 1, 2, 3, 4, 5, 6, 7 plus 7, right? So that's why what are the states allotted? -1, we have +1, we have +3, we have +5, and we have +7, right? So these many ways we can go for. Now here as well, we get one anomalous behavior, and that is shown by fluorine, the first atom of the table. Fluorine's configuration is 1s2, 2s2, 2p5. It ends in the second orbit, so there are no d orbitals. There are no d orbitals. We do not have any d orbitals in fluorine. So what have we learnt about not having d orbitals? When d orbitals are not present, you cannot achieve higher oxidation state. You cannot achieve higher oxidation state. So how does fluorine look like? It looks like 2s2, 2p5, 2s2, 2p5. So what are the possible conditions? If suppose, see, unpairing is not an option, but let's say an electron comes and sits in, it becomes -1 charge. Okay, what else can be a possible idea? What if that one unpaired electron leaves? If that electron leaves, it becomes +1. So can you see fluorine has only two oxidation states, -1, +1. And why is that happening? Because there are no d orbitals. And because there are no d orbitals, higher oxidation states cannot be achieved by fluorine. So anomalous behavior of fluorine and oxygen says the same thing. Smaller atoms, highly electronegative, have no vacant d orbitals. Therefore, they do not show higher oxidation states. Okay, now we are coming to the last group. What is our last group? Group 18. Yes or no? Group 18 general configuration is Ns2Np6. Let's see, let A be an element. Let A be an element in group 16. How do we represent it? Ns2, Np6, Nd0. Okay, so let A be there. Ns2, right? Np6. Problem is that there are all paired electrons. There are no unpaired electrons. All are paired electrons. So first things first, what do we need to start with? Unpairing. We start with unpairing. So let's unpair this electron. We have a vacant d orbital, we'll unpair it. So now how many unpaired electrons? 2. So what is the oxidation state? +2. Let's go to the next possibility. 2, 2, 2, 1 and 1. This is paired. Let's unpair it. When we unpair, when we open it up, make it singular. How many unpaired electrons do we have? We have 4 unpaired electrons. So oxidation state becomes +4. What is the next possibility? Do we have paired electrons? Yes, we still have paired electrons. So we are going to unpair it. The paired electrons are going to be unpaired. Okay. So what do we do? Which all unpaired we can see? 1, 2, 3, 4, 5, 6. So they can have a charge of plus 6. Next, what else? We have another paired electron. Pairing needs to be unpaired. Okay, so pairing needs to be unpaired. Okay. So how many unpaired? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So our group 18 will have common oxidation states as +2, +4, +6, and +8. Now, technically, group 18 are inert elements. They do not participate in reactions because they are already complete, right? Why do they need to unpair? Unless and until a huge amount of energy is gushed into them, which makes them reactive. No other parameter can make them reactive otherwise. Okay. But as the atomic size increases, let's say we have xenon. Xenon's atomic size has gone pretty huge, right? So that time xenon as an element can give you good oxidation states like +2, +4, +6. +8 rarely achievable. Okay. So group 18, not much on giving out ideas. Okay. They are actually inert. There's one way which I as a student used to remember. I hope it will help you as well. Okay, a simple way to remember for MCQs. NS2NP4, NS2NP5, NS2NP6. Okay, so what all? 2 and 4. Total makes it 6. So maximum achievable oxidation state could be +6. 2, 5. Maximum configuration can be achieved as +7. 2, 6. Maximum configuration is +8. Okay, so this is one way of going towards it. Another way is, you can see over here we have P4, P5, P6. We know P6 is the complete orbital state. Okay, no matter what, P6 is the complete orbital state. So your elements in P block, once they have crossed P3, they are in a rush to complete their complete oxidation. So if you see how many less than 6, 2 less than 6. How many less than 6? 1 less than 6. Okay, so there can be 2 plus 1 minus 1 plus 2 minus 2. This is another format of remembering. Again, I'll tell you these tactics I used to use when I was a student. Okay, and I was preparing for competitive exams and I had to know the oxidation states on my fingertips. Okay. Another way which you can go for, okay, is a good way actually, I feel, is for remembering the other ones. Now, here you can see 4 minus 2, see, 4 minus 2, 5 minus 2, 6 minus 2. This will also give you some hint. Okay, this will also give you some hint. 4 minus 2 is 2. 5 minus 2 is 3. 6 minus 2 is 4. And finally, P4, P5, P6. So I'm not sure how many of you would find this helpful, but I personally, when I was a student, this helped me a lot. These tactics build a lot of confidence in me that, you know, I need not memorize, neither did I have to sit and solve each element. So I hope you might also feel this is useful some or the other way, or else our general parameter of solving and calculating oxidation state works the best. With this, I hope you have understood. All the best for your upcoming exams. Signing off. Bye.